Good day, nanotech students. In continuation to our previous discussion, we'll talk about atomic packing factor and volume efficiency of a unit cell. Atomic packing factor is a measure used in material science and crystallography to measure the efficiency with which atoms pack together within a crystal structure. By definition, atomic packing factor is the ratio between the volume of the basic atoms of a unit cell to the volume of a unit cell itself. That is mathematically expressed in equation 1, where mu stands for the volume of the basic atoms in a unit cell, and the capital V stands for the volume of the entire unit cell. But the volume of atoms in a unit cell, that is mu, is mathematically expressed as n times the volume atom cell, where n, of course, stands for the number of atoms in a unit cell, and V is the volume of an atom. Then we can elaborate equation 1 by plugging this expression, and we obtain equation 2. Take the 3D simple cubic as an example in calculating the volume efficiency using the atomic packing factor. But first we need to calculate first the number of atoms in a simple cubic. Note that there are 8 edges in a simple cubic, and 1 atom is placed on each edge. So this 1 atom is shared by the neighboring unit cells, thus obtaining a fraction of 1/8. Overall, the number of atoms in a simple cubic is just 1. So let's proceed to finding the equation of the volume of a sphere that symbolizes the shape of an atom. Obviously, the volume of the sphere is just expressed in 4/3 pi r cubed. Furthermore, the edge length of a cube is shown in this figure and has the length of a. Hence, the volume of the cube is expressed in a to the power of 3. But at the edge of the length a, there are 2 atoms contact each other. So the edge length of this cell is just equivalent to the 2 atomic radii, such that the edge length a is now equivalent to 2r. Plugging the values of n, the volume of an atom in a cell, and the volume of the unit cell, we obtain the value of the atomic packing factor of a simple cubic with pi/6. Okay, and multiplying the result by 100 will obtain the volume efficiency of the simple cubic, having 52% efficiency. It means that 52% of the space of a simple cubic is occupied, while 48% is unoccupied. Among the 3 common unit cells in 3D, say those are the simple cubic, second one is the body-centered cubic, and the third one is the face-centered cubic. Among these 3 common unit cells, the simple cubic has the lowest volume efficiency. The higher efficiency, the percentage of the volume efficiency, means that uh, it leads to a stronger bonds between atoms or ions due to their close proximity, resulting in higher mechanical stability. It can also enhance the properties such as electrical conductivity, thermal conductivity, and optical properties. It often results in higher densities materials, which can be advantageous in various applications, such as structural materials or even materials that is used in electronic devices. In summary, higher volume efficiency in crystal structure indicates an optimal arrangement of atoms or ions that maximizes the occupation of available space. It leads to desirable physical and chemical properties. That's all for today, and thank you for watching.